Hello and welcome to this course on MATLAB programming for numerical computations. We are in week 10 of this course. In week 7 and 8, we had introduced you to ordinary differential equations, initial value problems. In this week, we are going to take boundary value problems for solving ODEs. Okay. So, differential equations are very important in science, engineering and mathematics. Differential equations comes in various forms: ordinary differential equations and partial differential equations, as well as something called differential algebraic equations. Okay. We covered ODE-IVP in single variables in week 7. Thereafter, we extended it to ODEs in multiple variables and for stiff systems in week 8. In this week, we are going to cover first ODE boundary value problems, and then we are going to cover differential algebraic equations. Next week, we are going to focus on partial differential equations. Okay. So, without a further ado, let me introduce you to ODE boundary value problems. Okay. Now, for this, I will recap something that we had done in week number 4. In week number 4, we had talked about a heated fin or a heated rod, which basically means that, let's say we have a rod like this end is kept at 100 degrees Celsius, this end is kept at 25 degrees Celsius, okay. And because this rod is hotter than the surroundings, it loses heat to the surroundings, okay. And this loss of heat is given in terms of heat transfer coefficient multiplied by area per unit volume ratio T minus T of ambient. Okay. So, the overall model for a system like this is given by d square T by dz square, this multiplied by the thermal conductivity minus H multiplied by area per unit volume T minus Ta. Okay. And this we can rearrange this in the form d square T by dz square. Okay, we can take this on to the other side and divide by k, and we will get this as equal to gamma multiplied by T minus Ta. Okay. So, that is going to be the overall equation for a heated rod or a heated fin. Okay. So, A by V is area per unit volume, and if that is a cylindrical rod, then A by V is 1 by d, okay, where d is the diameter of the rod, right. So, that is how we actually have the overall system. Now, what we had done in week 8 is we were able to convert a second order ordinary differential equation into a series of first order ordinary differential equations. How? By say by defining let us say capital Y or small y, let us say small y as dt by dx, and therefore, or dt by dz, let us call it, let us make this z, that is what we have used, and then dy by dz is going to be gamma t minus Ta. Okay. So, that is how we had done in week number 8. Now, what is the difference between initial value problems and boundary value problems? In week number 8, what was given to us is all the conditions were given at time t equal to 0. Okay. In boundary value problems, one of the boundary conditions is given at this boundary, we will call that as a boundary A, and another condition is given at this boundary, we will call that as boundary B. Okay. Because the values or the boundary conditions, because it is a second order differential equation, we require two boundary conditions. Because the two boundary conditions were given at two different locations, it becomes a boundary value problem. If both the boundary conditions were given at the same location, for example, T at location 0 was given and dt by dz at location 0 was given, that would become an initial value problem, which we already covered in week number 8. Okay. So, to recap, in addition to the equation of this type, we are given one boundary condition, BC1 is given at at z equal to a and BC2 given at z equal to b, okay, or we can call this as given at z equal to z naught and given at some z equal to z1. Okay. So, that is how we have the boundary conditions specified. Okay. So, this week what we are going to do is we are going to find ways of how to solve this boundary value problem. Okay. The first approach to solve this boundary value problem is using inbuilt MATLAB solvers. The solver that we are going to use is BVP 5C. Okay. So, BVP stands for boundary value problem 5 because it is a 5th order boundary value problem. Okay. Thereafter, in the next video, I am going to use finite difference approach in order to solve this same problem. Okay. And finally, we are going to solve using a method called shooting method. Now, let us get on to using the MATLAB boundary value problem solvers. Okay. Now, how are the MATLAB boundary value problem solvers laid out? They are laid out, the first part is the domain equations. It is laid out exactly the way we had done it in week number 7 and 8. That means, we have to express the overall domain equation in the form of d capital Y by dz, I will write that as zz equal to some function z comma y. Okay. The next thing is at boundary condition 1 is going to be 0 equal to some function g, let us call it as g1 of y0 comma y1. Okay. BC2 is going to be 0 and some function g2 y0 comma y1. Okay. Now, for example, what does this mean? So, if this is the boundary condition and this is the other boundary condition, the first boundary condition will be written as t minus 100 equal to 0. The second boundary condition is going to be written as t minus 25 equal to 0. But which t? This is t at z equal to 0 and this is t at z equal to L. Okay. So, this is just going to be t0 minus 100 equal to 0 and this one is going to be t1 minus 25 equal to 0, okay, where T1 is the temperature at the other end. Okay. So, now let us go on to MATLAB and try to solve this rod conduction problem using the MATLAB boundary value problem solvers. Okay. Let us call this as edit rod conduct.m, okay, and conduction in a rod. Gamma, I think that we had used earlier was 4.0, TA is 25, T0 is equal to 100, T1 equal to 25. Okay. These are the overall conditions. Okay. So, let us write down the function and the functions. The first function for, so function dy dz equal to rod fcn z comma y. Let us call that parampar. Temperature T is y1, small y is capital Y2, okay. So, what do we have? We have dy dz 1 comma 1 equal to and then dy dz 2 comma 1 equal to, right. So, the first guy is dt by dz. So, dt by dz is y. So, we will just write that as y, and d small y by dz was nothing but gamma multiplied by T minus TA, which is T ambient. Okay, and end. Okay, so that's the overall function that we have. So that's the conduction in the rod, starting with initial temperature as T equal to 100, and the temperature at the other end is T1 equal to 25. Length of the rod is 1 meter. So these were the various data that were given to us. Okay, so now let us look at help BVP 5C. Okay, so BVP 5C, ODE fun, boundary condition fun, and the initial solution. Okay, so that's what we basically need. So we have d capital Y by dz is equal to f of x comma y comma param, and 0 equal to boundary conditions at the point A and point B. Okay. So, we need a boundary condition function also. So, let us write this out. Function residual is equal to rod BC for boundary conditions, and what do we have? We have T0, T1 and par. Okay. So, T0 is the boundary condition at length equal to 0, T1 is boundary condition at length equal to 1. Okay. So, what is our boundary condition? So, res 1 comma 1 is the first boundary condition, res 2 comma 1 is our second boundary condition. So, let us look at what was the first boundary condition. The first boundary condition was T0 minus 100 equal to 0, right. So, that was our first boundary condition. Now, what is T0? Okay, I made a mistake and I will come to that. T0 is nothing but y1 at location z equal to 0. Okay. T1 is nothing but y1 at location z equal to 1. Okay. What do I mean by that? We have this entire rod, okay. Because we are solving the equation dy by dz, we have y that is over here, we have y that is coming over here, we have y that is coming over here, and so on up to y that we are going to have over here. Okay. Now, this y is going to be capital T and small y, this y is going to be capital T and small y. Okay. This as at location z equal to 0, this is at location z equal to 1. T minus 100 is the value at this point, T minus 25 is the value at this point. Okay. So, that is what I should have written. It's not T0 and T1. It's y0 and y1. Okay. y0 1, this is the temperature, minus 100 is the first boundary condition, y1 1 minus 25, that is the second boundary condition. Okay. So, this is the rod BC. Okay. We do not need the parameter over here, that is perfectly okay. Okay. Now, to solve using to solve using BVP solver, let's look at what we need. We have a solution. This is the format. So y sol equal to BVP 5c. ODE function is at z comma y sorry, param should not be here. Y init, where y is the initial solution. Okay. Now, let us say we want the solution at z equal to, let us say we want number of points is 10. So, the step size is h equal to L by n. Okay. So, z is going to be equal to 0 in steps of h up to L. Okay. So, that is the value of z. Let us say we want to initialize everything uniformly as at say 50 degrees Celsius. Okay. So, T initial equal to 50 and y initial equal to 0. So, that is, or dt by dz, because we know that the temperature is going to fall because one end is hot, the other end is cold. So, as y is increasing, temperature is falling. So, we will give a negative value, say minus 50. Okay. That is y initial, this is t initial. Okay. Remember, capital Y is different than small y. So, y init. Now, the way you can have init is using a initialization function. Okay. BVP init is the function that can be used for initialization, and let us look at help for BVT init. Okay. So, BVT init is you give your z values and your y init values. Okay. So, BVP T z comma, now what is y initial values? T initial semicolon y initial. Okay. That is going to be y init. Okay. So, let us save this. Let me go over what we have actually done. So, what we actually did is we created a function rod FCN. Okay. Rod FCN has these two guys, where y is nothing but t comma y. Next, we have rod BC okay. Of course, equal to 0 we do not give, this is what we need to give. Now, this guy is nothing but y01 this guy is nothing but y11. Okay. So, that is our rod BC. Our initial conditions, we say that throughout this rod, let us say T was 50 degrees Celsius and dt by dz was minus 50. Okay. So, which means y initial minus 50, and let us say we wanted the solution at every 10th at 10 points in the interval, that means at z equal to 0, z equal to 0.1, z equal to 0.2, 0.3 and so on up to z equal to 1. Okay. So, therefore, we said that z span is going to be 0 to h to 1, where 1 is nothing but L. Okay. So, that is how we had these initial conditions put up. Let us go back to MATLAB and see if that is exactly what we have done. Okay. So, function is rod FCN, dy by dz is this, dy by dz 2 comma 1 is this guy. Okay, that is fine. Y gamma multiplied by t minus ta, right. Okay. Residual, the first residual is y01, that is temperature at location 0 minus 100. The second guy is temperature at location L equal to 1 and minus 25. Okay. Initialization, T initial is 50, Y initial is minus 50. So, this initial condition, this guy is nothing but 50 minus 50. Okay. So, yeah, that is what we have. So, let us now run this code and see what we get. Okay, we get an error. Let us see why we have an error. Unrecognized function or variable param. Okay, I haven't defined param, I am sorry about that. Actually, this is how it should have been. Param dot gamma, param dot ta. T0, T1 we do not need, so we can actually delete that. We do not need to do it, we do not need to give those values twice. So, we will delete that. Even if you leave it, it is not going to cause any error, but the right thing to do is delete it, because we do not want the same value defined at two different locations. Run. Okay, we get one more error. Oh, gamma is another function. Okay. Oh, this should have been param dot gamma, par dot gamma, par dot ta. We actually do not need the par over here. I can delete this and I can delete this as well. Okay, that hopefully should work. Let us see if it works. Okay, yeah, so we have our ysol. Let us see what ysol says. Ysol is you have x and y. Tsol is nothing but ysol dot y 1 let us plot. Okay, so this is how the temperature changes with location. So, you have the rod, the temperature drops from 100 degrees Celsius to 25 degrees Celsius along the rod of length 1. Okay. Now, let us look at an interesting problem. So, what happens if you increase the gamma? What do you mean by increasing the gamma? Increasing the gamma means either the heat losses are increased or the thermal conductivity is decreased. So, let us consider the case where the heat losses are double. So, if we have doubled the heat losses, let us say we have gone from gamma equal to 4 to let us say gamma equal to 8, what do we get? So, let us do this. Plot the results. And let us say hold on. Okay. So, let us run this and see what happens. This we are now running for gamma equal to 8. Okay. What do we expect to happen? Think about this blue line. The next red line, will it come above this line? Will it come below this line? Will it come on this line? Think about this. If there is greater amount of heat loss, then the temperature drop from 100 degrees Celsius will be faster. So, the red line is going to come below that line. So, that is what we expect from the physics. Let us see if that is indeed what we get. Okay, and yes, indeed we do get our red line that goes below our blue line. That is what happens as you increase the heat losses. Okay. So, with that I come to the end of this lecture. The first option we covered for solving ODE boundary value problems is using the solver BVP 5C. If you want to learn a bit more about this, please go through the documentation of MATLAB. MATLAB has also a solved example, and that is what you will use in order to understand how the boundary value problem solver works. Okay. Again, to recap, what we have over here, what we get as an approach is to define the function, to define the boundary conditions, and to initialize the solution and then solve the problem using BVP 5C. Okay. So, with that I come to the end of this lecture. I hope you enjoyed watching this lecture on ODE boundary value problems. In the next video, I am going to talk about the finite difference approach to solve ODE boundary value problem. Thanks and see you in the next video. Bye.